The p-value, the statistical value that has been misused for 100 years, the thing that's completely ubiquitous in statistical testing, yet fundamentally used incorrectly by the majority of people that use it. So much so that leading statisticians have called for the complete abandonment of the phrase statistically significant, which is a common conclusion to using the p-value. Now, I'm going to explain the p-values in a non-scary way, and I'm going to build into it and reiterate. So stick with me, hang out for a little bit, and I think you'll be cool with it by the end. So let's say my wife wants to know if I went to the movies, but I'm at a cell service, so she just can't call me and ask. She does, however, see a burrito wrapper on my desk, and she does the burrito math, and it turns out that if I didn't go to the movies, there's a 5% chance I ate a burrito. That was a really big setup just to say if I didn't go to the movies, there's a 5% chance I ate a burrito. If there's a 5% chance I eat a burrito if I don't go to the movies, and I ate a burrito, does that mean there's a 95% chance I went to the movies? Well, no. What if I never eat burritos on days I go to the movies? The burrito math only indicates the probability of burrito eating when I don't go to the movies. Burrito math doesn't say anything about when I do go to the movies. So how can my wife tell if I probably went to the movies? How do we go from no movie, 5% chance of burrito eating, to probability I went to the movies if I ate a burrito? Well, what is the probability I eat a burrito if I go to the movies? If we know that, we can compare it to the 5% when I don't go to the movies. For example, if I almost never eat a burrito on movie day, even though there's only a 5% chance on non-movie days, that's a greater chance than almost never, right? 5% is more than, approaching zero. So me eating burrito makes it more likely if it's a non-movie day. If on the other hand, I almost always eat a burrito on movie day, the eaten burrito would indicate I probably went to the movies, because that's a much higher probability than the 5%. By the way, it's the same thing if you look at the thing from the reverse direction. If I almost always eat a burrito on movie day, and I ate a burrito, does that say I probably went to the movies? Nope, because maybe I almost always eat a burrito every day, movie days included. Now, you may have found this reverse direction a little bit more straightforward. And you might say, why on earth, Alex, didn't you just start with that? Well, because the first direction I talked through is what we're doing with statistical testing. The eaten burrito is your data. The burrito math is the determining of the p-value. And the 5% chance is the p-value. So what is a p-value? What is that 5% chance? The p-value is the probability of eating a burrito on non-movie days. Or the p-value is the probability of getting your data if nothing happened. And by nothing happened, I mean there's no change, no correlation, not a difference. It's basically a stand-in for whatever's happening depending on that statistical test, whatever you're testing for. So we need to compare the p-value to something. The major fail for the last century was to compare it to an arbitrary significance level, which, despite its official sounding name, is really an amorphous thing. A more appropriate name might be the we stop caring that we aren't comparing the p-value to anything level. So what do you do with p-values, going forward? First, learn what the p-value actually means, and hopefully this video served that purpose. You may need to watch it again because it is still sort of confusing, that forward direction. And also, depending on how ingrained the concept of statistical significance has been with you over time, it can make it harder to unlearn that. Second, now that you know what the p-value actually is, you can make a case-by-case assessment. Situational awareness. If we integrate a little Bayesian statistics, not everything, just sort of a flare of Bayesian statistics, we can compare the p-value to the probability of getting our data if something truly happened, right? That correlation, a change, a difference, whatever, the truly happened thing. Estimating that probability can be tough, however, but it's very possible you're already doing it to some extent for at least some of your experiments. Say you run an experiment to see if raising the temperature 10 degrees on a heat sealer will impact the seal strength. Well, physics, aka first principles, and if you've honestly been anywhere near a heat sealer, and it's called a heat sealer, all suggest temperatures impact seal strength. Now, will the 10-degree change in temperature have a noticeable impact? I don't know. You're going to have to run an experiment to find out. But temperature impacting seal strength is equivalent to me always having a burrito on movie day. If you ran the experiment and got a p-value of 0.02, you can be pretty sure the temperature change, it actually had an impact and it wasn't random chance, right? However, if you get a p-value of 0.4, it could have been because the temperature changed, but there's a 40% chance of getting those results if the temperature change didn't impact the seal strength. Basically, it would be inconclusive. And in other words, if the science clearly suggests a change, you aren't making, too much of a leap. You're not taking on too much risk by going with that low p-value. You've sort of already integrated the comparison probability into your thought process, into running the experiment. Also, a lot of time when we're running experiments, it's because we suspect factors will have an impact, or we have a previous test that says so. Basically, we think for some reason it's good to test. Try to be clear about what that reason is, because that's effectively your comparison probability. And if, hey, you can put a number to it, even better. Now, if you don't have any pre-existing knowledge that the factors you're testing probably impact the thing you're measuring, aka the response, you need to estimate the probability some other way, that probability that we're going to compare to the p-value. Now, that goes in too many directions for me to fit in this one video, but a big reason why using first principles and empirical work together is important is because we're bringing in the prior knowledge to support our statistical analysis. It's much more powerful and insightful that way. Lastly, the actual value of the p-value matters. Whatever the comparison probability is that you find, and again, it can be very tough, the lower the p-value, the more likely that something happened, right? That change, that difference, that whatever. So, in summary, you don't need to throw out all the experiments you've ever run. You do, in all future experiments, need to consider the probability you get your results, assuming there was truly a change. You may want to review some select experiments that were either problematic, exceptionally important, or for which you don't really understand the underlying science. A quick commentary. How to best use the p-value, whether to even use the p-value, Bayesian versus frequentist approaches, hybridizing the two, new statistical techniques. There's a lot of stuff up in the air right now, and it's going to take a little while for it to settle out, actually assuming it does. So I focused this video on what you can do now, practically speaking, on a project. You're on a project right now, what can you do? There's a reasonable chance that in 5 years down the road, maybe less, I'll recommend a different approach. But with where inferential statistics is currently at, this is what I feel is the best approach, and one you can run with, for now. Anyway, if you want to read more, I'll link to the best summary I've found for what the statistical situation is right now. I'll put that in the description. And that's it. That's p-value. Please like, please subscribe, please share. All are very helpful, and I'd appreciate it very much. Thanks.